Okay, so this is Unit 4, and it is bonding and naming compounds. In this first lesson, we're going to look at how energy changes in a compound as bonds are broken and new bonds are formed. And we're going to begin looking at two major categories of compounds, which are ionic, in where electrons are transferred, and molecular, which is also called covalent. Those two terms are synonymous, where electrons are shared. So let's do a little review. From a couple of units ago, we learned what a compound was. Compound is a substance that has atoms of two or more different elements chemically bonded. And what is a bond? A bond is forces of attraction between the protons, which are positive in the nucleus of one atom, and the electrons, which are negative, of another atom. So it is the forces of attraction between my protons and your electrons, basically, when you're talking about two different atoms. And remember, it's only the valence electrons, those electrons in the outermost shell, that participate in bonding. No kernel electrons are involved in bonding. Bonds are formed as a result of a chemical reaction. So we've been talking a lot about the valence electrons, and we've also been talking about that all atoms want to either give up electrons or gain electrons in order to have a full octet. From now on, when I write the word reaction, I'm going to abbreviate it as RXN, just so that you know, if you see that that's reaction. In order to talk about this, we have to talk about the law of conservation of energy, mass, and charge. During a chemical reaction, energy, mass, and charge cannot be created or destroyed. So what I start with, I must finish with. It can be arranged, so mass can be arranged in one form or another. Energy can be transferred from one substance to another. Electrons can be gained or lost, but the total amount of energy, mass, and charge of what I start with and what I finish with must be the same. That means that all three are conserved. And this is really important for you to understand. So we know that we have an octet rule. Atoms bond together to get 8 valence electrons. This is a review around them. 8 is great. Okay. Noble gases already have 8 valence electrons. That's why they don't react or bond with any of the elements. There are a couple of exceptions in which they will, and we'll talk about them later. But generally speaking, they have 8. They don't want to give up electrons. They don't want to gain electrons. Which noble gas, helium, neon, argon, or krypton, would be most likely to form a bond with another element? So I want you to look at your periodic tables. Out of helium, neon, argon, and krypton, what did you find out? Well, hopefully you said it was krypton. And if you look at your periodic table, the reason being is it has the most shielding, or it has a non-zero oxidation number. So out of these 4, it has the most shielding, and that's due to the number of principal energy levels. I'm just going to write in parentheses more PELs. And also, if you look at it, it has a +2 oxidation state listed, which means that under the right circumstances, it will bond with something. So when we look at these 5 elements, Na, O, F, P, or S, what would be the most likely to form a bond with krypton? Well, what you want to look at is, remember, electronegativity is attraction for electrons in a bond. So which one of these is going to have the highest electronegativity? And that's going to be fluorine, because I told you that fluorine was the bully of the periodic table. It has the highest electronegativity, and that is 4. So it's going to be fluorine. And the reason why is it has the highest electronegativity. And I'll put 4.0 in parentheses. There we go. So let's look at the changes in energy when we bond. A spontaneous bond formation. So remember that the word spontaneous means that it happens by itself. Okay? If you don't know what spontaneous means, write that over off to the left. Happens by itself. Spontaneous bond formation equals energy that is released. And this happens when we go from, when is energy released? When we go from high energy, unhappy atoms because it's unstable, to low energy, happy atoms because that's where it's more stable. So creating a bond creates stability. So here you might want to put unstable, because that's the excited state, they're unstable. And here you might want to put stable. So creating a bond creates stability. Exothermic is when energy is released as a product. So when we release energy, we refer to this as exothermic. And if we were looking at a reaction, you'd have A plus B yields C plus energy. Energy is a product. It's being released. Energy is on the right side of the arrow. And here's an example. You have calcium chloride, which is a salt, plus sodium carbonate, which is baking soda, and that's going to produce calcium carbonate, carbon dioxide, sodium chloride, and heat. So, right here, A plus B yields C. Here you have bonds forming. It's exothermic, and when two things come together, this is kind of like marriage. This type of, I'm going to teach you this a little bit later on in another unit. This is called synthesis. I'm just laying a little groundwork. And synthesis really means to make or put together. And that's what's happening here. We're putting A and B together and we're forming C. We're forming bonds, which is an exothermic reaction, and we're releasing energy. And we know that it's exothermic because the energy value is on the right side of the arrow. Now, breaking bonds is not spontaneous. So, if in a spontaneous reaction energy is released, in a non-spontaneous reaction, it should make sense that energy is absorbed or another good word is consumed. We go from low energy, which is happy, which is stable, to high energy, which is unhappy, which is unstable. So ripping two atoms apart takes energy. I want you to think of it this way. If I'm standing in the front of the room and I look at the back window of the classroom, it's not going to break on its own, correct? But if I pick up a stapler and I hurl it at the window, it's going to break. Now there's a couple of reasons that this is happening. One is I'm transferring my energy to the stapler, so the stapler absorbs my energy, and when the stapler hits the glass absorbs the energy, and the window breaks. So to help you remember about breaking bonds, think of the window. The window doesn't break on its own. The window has to absorb energy in order to break the window, just like breaking bonds has to absorb energy in order to break the bonds. So endothermic is when we absorb energy. When energy is absorbed meaning consumed, or needed as an ingredient to fuel the process. Notice now that energy is on the left side of the arrow. This is also when I take one thing and I break it into two things, this is also known as a decomposition reaction. And to break apart. So this is the opposite to break up or apart. So this is the opposite of synthesis. Synthesis means to make or put together. Energy is released. This is decomposition. Energy is absorbed, which means that we're breaking apart or breaking something up. An example of this might be an ice pack. When you get one of those instant ice packs and you pop it and shake it, the chemicals combine, bonds are broken, and energy is consumed. The ingredients in that cold pack absorbs the energy from the surrounding environment, and the temperature of the pack decreases. It feels cold. The reason why it feels cold is because when you put it on an injury, heat travels from high to low. So what happens is the heat from your body is being absorbed by the ice pack. And that's why you feel cold. Okay, let's briefly talk about the two most common types of compounds. Ionic. Ionic is between a metal and a non-metal. Or it can be between some other types of combinations are a metal and polyatomic ion, which I'm going to talk to you about. You might want to get out your reference table and look at these. These are in table E. Or a or two polyatomics. And it also could be, no, I think that's about it. So let's look at these individually. First, let's look at a metal and a nonmetal. We know that metals like to lose an electron. So sodium is 281. It wants to give up that 1. Chlorine is 287. It wants to gain 1. So what's going to happen here? Sodium gives up its 1 electron and forms a positive ion. Chlorine, on the other hand, takes that from sodium and it forms a negative ion. So now I have a negative ion and a positive ion, and they're attracted to one another and they form a bond. We always put brackets around the ion that's gaining the electrons, and then each of the ions gets their respective charge, because it's the opposite charges that then causes the sodium ion to be attracted to the chlorine ion and form a bond. Now, I want to tell you something, and I don't want to confuse you. You have a polyatomic ion. A polyatomic ion is an ion that has a charge within itself. And polyatomic ions are what we say covalently bonded. Because if we look at just NO3-, which is what this is, NO3, it has a -1 charge. It's not showing that here. I'll show you in a minute. This is made up of all nonmetals. All nonmetals. And nonmetals form a covalent bond. Just like an ionic bond is a metal and a nonmetal, there's a transfer of electrons. This is a covalent bond, which we're going to talk about in a little bit. But electrons are shared. So what happens is, to explain an advanced concept to you right now. When I want to figure out how to draw NO3-, I have to look at how many valence electrons are involved. So what I know is nitrogen has 5. And I know that I have 3 oxygens, and each oxygen has 6 valence electrons. Plus this minus sign tells me that the ion gained an electron. So I've got 3 times 6, which is 18, plus 5, which is 23, and 1 equals a total of 24 electrons. And remember, each atom wants 8. So how can I draw NO3- so that everybody's happy? Well, electrons are constantly moving. So what I'm going to do is I'm going to draw my 3 oxygens, and I'm going to explain this in just a minute. Okay, so first of all, just give me a minute. I want to explain that when you see a line like that, a bond line, that equals, so a bond line equals 2 electrons. That's a single bond. We have things that are called, so this is a single bond. I'm going ahead a little bit so that hopefully that helps you understand this. So this is a single bond. This is considered a double bond, so that equals 1, 2, 3, 4 electrons. So this is a double bond. And then we also have something called a triple bond, and that's going to be 6 electrons, and that's a triple bond. So when you see this one single bond line, this represents 2 electrons. So if I count my electrons right now, 2, 4, 6, 8. This oxygen's happy. 2, 4, 6, 8. That oxygen's happy. 2, 4, 6. Now, I could put 2 electrons here. I'm going to do that, right? 2, 4, 6, 8. So we've got 8, 8, 8, 24. I've used all my electrons. But the oxygens are happy, but the nitrogen isn't, 2, 4, 6. So what I can do is, instead of putting 2 dots here, I can turn this into what's called a double bond. So now nitrogen's got 2, 4, 6, 8. It's happy. This oxygen is happy. 2, 4, 6, 8. Everybody's happy. And this is what would be considered an NO3 minus. An NO3 minus drawing of just the ion. But now, when this NO3 wants to bond to sodium, remember sodium wants to give up an electron. It has an electron to give up. So we've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. All right? So this is what I drew. This came over here. And what happens is you get Na plus, and you get this drawing that I drew over on the right. This is going to be the hardest unit for some of you, and we are going to go slow, I promise. So you get sodium nitrate. The bigger picture that I want you to understand right here, I'm not going to ask you to draw this B, okay? I need you to draw stuff like an A. When I have a metal and a nonmetal, or a metal and a polyatomic, it is, or two polyatomics, which I haven't showed you yet, it is an ionic bond. There is a transfer of electrons from one atom or polyatomic, to another. That's the big picture that I need you to understand. Here I have a polyatomic ion actually, so I didn't list this one up top. This is a polyatomic ion and a nonmetal. This is NH4 plus. How did I know how to draw this like this? Nitrogen's got 5 plus 4 times, each hydrogen has 1, so 4 times 1. This plus means it lost 1. So it's 5 plus 4 is 9, minus 1 is a total of 8. 2, 4, 6, 8. Nitrogen's happy. Remember, a bond line equals 2 electrons. Nitrogen's happy. It's got 8 electrons. Remember, hydrogen is the exception to the whole rule. H only wants 2. And that's what it has. This H is sharing 2 right there. This H is sharing 2 right there. This H is sharing 2 right there. And this H is sharing 2 right there. So when it forms a bond, it's going to give this electron to chlorine. Do you see how chlorine now has 8? One of these, could be any one, came from the ammonium ion. Here we have 2 polyatomics. Here we have ammonium, which is NH4, and nitrate. So this is NH4 plus, and this is NO3 minus. There's the NH4 plus, the NO3 minus, and they form a bond. So I'm just going to go back to my list here. We've got a metal and a nonmetal is one case, a metal and a polyatomic, 2 polyatomics, and the last type of ionic is a polyatomic and a nonmetal. Now, I don't want to confuse you, because I'm sure you're confused already. When you have a metal and a nonmetal, it's strictly an ionic compound. Anytime you have a polyatomic ion involved, you have 2 types of bonds going on. Remember I told you that the NO3 is all nonmetals? So you have covalent bonding with the nonmetals, but then you have a transfer of electrons to the polyatomic ion, which is ionic. So the last thing that I want to note in this section, which is very important, anytime a polyatomic ion is involved, you have both ionic bonds and covalent bonds present. And that's because within the polyatomic you have covalent bonds, but you have an overall transfer of electrons from one to another. All right, now let's look at covalent. Covalent is compounds formed when two or more nonmetals share electrons. Covalent is also called molecular. They use these terms synonymously on the regions. So you have to know that covalent equals molecular. So here you have methane, CH4, all nonmetals, water, H2O, and ammonia, NH3. How do I decide how to draw these? Well, carbon's got 4 valence electrons. 1, 2, 3, 4. Here comes H with 1. Here comes H with 1. Here comes H with 1. And here comes H with 1. I can then replace this X and this dot. I use X's and dots just to show you. The dots are the 4 valence from the carbon, and the X is the valence from the hydrogen. I can then replace that with what you see above, which is just a bond line. This is basically a structural diagram. And this over here that I drew was the Lewis dot diagram. It all depends on what they're asking for. Water has got 6 valence electrons. There they are. H comes in here with 1. H comes in here with 1. And then we just replace these bond lines. And these are 2 non-bonded pairs of electrons. There's nothing else there. Ammonia, nitrogen's got 5. 1, 2, 3, 4, 5. H came in here with 1. H came in here with 1. And H came in here with 1. Okay, so let's just review this. Ionic versus covalent summary. A metal and a nonmetal is going to be ionic. A metal and a polyatomic is going to be ionic. That's the main thing. But it's also covalent, and that's due to the polyatomic ion. A nonmetal and a polyatomic ion is going to be ionic, overarching, but because of the polyatomic ion, it's also covalent. Polyatomic and polyatomic, there is a transfer of electrons from one polyatomic to another, so that's transfer. So you've got ionic, plus they're polyatomics, so you also have covalent. Nonmetal and nonmetal, covalent. Okay, that's it for this lesson.